In this session, we will go through the fundamental steps of integrated circuit fabrication. Starting from a silicon wafer, we will follow the sequential processes: wafer preparation, mask making, lithography, oxidation, doping, etching, polygate formation, and metallization until a fully functional IC is ready. Each step will be explained in terms of its physical mechanism, process parameters, and role in semiconductor device manufacturing. Silicon is chosen due to its abundance, excellent semiconductor properties, and the ability to grow high-quality SiO2 for device insulation. Wafers are prepared as thin discs of intrinsic silicon, typically with diameters ranging from 70 m to 300 m and thickness less than 1 mm. Fabrication involves creating identical ICs across the wafer surface. Post-fabrication, electrical testing identifies functional and defective dies. Separation into individual dies is carried out through high-precision mechanical sawing using diamond-tipped blades. Integrated circuit fabrication is a sequence of additive and subtractive steps. Wafer processing prepares the substrate. Mask making generates photomasks for defining patterns. Photolithography transfers patterns onto the wafer surface. Oxidation creates insulating or masking oxide layers. Diffusion or ion implantation introduces dopants. Etching selectively removes materials. Polygate formation creates MOSFET gates. Metallization provides electrical interconnections. The sequence ensures proper alignment, layer integrity, and functionality. Integrated circuit fabrication is a sequence of additive and subtractive steps. Wafer processing prepares the substrate. Mask making generates photomasks for defining patterns. Photolithography transfers patterns onto the wafer surface. Oxidation creates insulating or masking oxide layers. Diffusion or ion implantation introduces dopants. Etching selectively removes materials. Polygate formation creates MOSFET gates. Metallization provides electrical interconnections. The sequence ensures proper alignment, layer integrity, and functionality. In common man language, fabrication is like building a skyscraper. You first prepare the land, which is equivalent to wafer processing, then create blueprints, which is equivalent to mask making, then mark the layout, which is equivalent to photolithography, then build walls, which is equivalent to oxidation, then add plumbing and wiring, which can be seen equivalent to doping and metallization, and then finally do the finishing touches. Each step builds on the last, and missing one can collapse the whole structure. In electronics, a wafer is a thin slice of semiconductor, such as a crystalline silicon, used for the fabrication of integrated circuits and, in photovoltaics, to manufacture solar cells. Wafers are manufactured from single crystal silicon ingots grown using the Czochralski or float zone methods. The ingot is sliced into wafers using a diamond saw. Subsequent lapping and chemical mechanical polishing, CMP, produce a defect-free, ultra-flat mirror surface essential for submicron lithography. Flatness specifications are extremely tight to ensure precise alignment between multiple layers in IC fabrication. One can think of the wafer as a mirror-polished plate made from pure silicon. It's incredibly flat. Analogously, if we consider a wafer up to the size of a football field, the height variation would be less than the thickness of a hair. This smoothness is critical because we're going to build structures only a few nanometers thick on it. The RCA clean is a standard set of wafer cleaning steps which need to be performed before high-temperature processing steps, oxidation, diffusion, CVD, of silicon wafers in semiconductor manufacturing. Werner Kern developed the basic procedure in 1965 while working for RCA, the Radio Corporation of America. It involves the following chemical processes performed in sequence. 1. Removal of the organic contaminants, organic clean plus particle clean. 2. Removal of thin oxide layer, oxide strip, optional. 3. Removal of ionic contamination, ionic clean. Analogously, think of an unclean wafer like your kitchen counter before you start cooking. If crumbs are present, the dish can fail. SC1 is like a soap plus scrub that removes grease and crumbs, organics and particles. SC2 is like a heavy-duty metal cleaner that removes metallic stains. HF is like briefly wiping off the top varnish. It strips the native oxide. Time and temperature matters. Hotter or longer is more aggressive but can also damage surfaces. Each fabrication step requires a specific mask pattern to define the regions for material addition or removal. The complete chip layout is decomposed into several mask layers corresponding to diffusion areas, polysilicon, metal interconnects, and so on. Electron beam pattern generators write these patterns on chromium-coated glass substrates coated with photoresist. The CI format serves as the standard interface between CAD layout and mask-making equipment. High precision in mask fabrication is critical to prevent pattern distortion. Analogously, one can say that masks are the blueprints of our city. Each floor of the building has its own plan, that's why we have multiple mask levels. A pattern generator, like a super-precise printer, transfers these plans onto glass plates coated with a light-sensitive layer. The CI format is like the PDF of the chip world, a universal way to send designs to fabrication tools. The fabrication of MOS structure requires several chemical processing steps. Lithography. Lithography is used to selectively process the layers where the 2D mask geometry is copied on the surface. The surface of the wafer is coated with a photosensitive material, the photoresist. The mask pattern is developed on the photoresist with UV light exposure. Photolithography employs optical projection systems to transfer mask patterns to a photoresist-coated wafer. The photoresist, a light-sensitive polymer, undergoes a chemical change upon UV exposure. Positive photoresist becomes soluble in the exposed regions, negative photoresist hardens when exposed. Alignment marks ensure precise overlay between successive layers. Soft baking removes solvents, development removes soluble regions, and hard baking improves adhesion and etch resistance. Analogously, one can say that photolithography is like using a stencil and a flashlight. We coat the wafer with a light-sensitive chemical called photoresist, shine UV light through the mask, and develop the exposed parts to reveal our pattern. Positive resists remove exposed areas, negative resists harden when exposed. Just like photography, the quality of the pattern depends on exposure and focus. Oxide growth. Oxidation of the silicon surface creates a SiO2 layer that acts as an insulator. Oxide layers are also used to isolate metal interconnections. Thermal oxidation is carried out in high-temperature furnaces, 800 to 1100 degrees C, in an oxygen or steam atmosphere. Dry oxidation yields high-density, uniform oxides used for thin gate dielectrics. Wet oxidation, using steam, achieves faster growth rates and is preferred for thicker field oxides. The oxide layer serves multiple purposes: electrical insulation, diffusion mask, and surface passivation. Analogously, oxidation is like putting a protective glass coating over wood. In our case, we heat the wafer in oxygen or steam, and the surface silicon reacts to form silicon dioxide. Thin, perfect glass, like a window pane, comes from dry oxidation. Thicker, faster growth, like a frosted glass wall, comes from wet oxidation. Ion implantation. Ion implantation is used to add doping materials to change the electrical characteristics of silicon locally. Deposition. While some of the structures can be grown on silicon substrate, most of the other materials, especially metal and oxide, need to be deposited on the surface. In the pre-deposition step, the wafer is exposed to a dopant source, either gaseous, solid, or liquid, at elevated temperatures. Dopant atoms diffuse into the silicon surface. In the dry-veen step, the wafer is heated in an inert atmosphere, allowing dopants to diffuse deeper while reducing surface concentration. Control of temperature, time, and ambient is critical to achieving desired junction depths and dopant profiles. Diffusion is like marinating vegetables. First, you coat the surface with seasoning, dopants, that's pre-deposition. Then you let it soak in with heat, that's dry-veen. Over time, the flavor, dopant, penetrates deeper, changing the taste, electrical behavior of the vegetable, silicon. Etching. Etching is a common process to pattern material on the surface. Once the desired shape is patterned with photoresist, the unprotected areas are etched away, using wet or dry etch techniques. Etching selectively removes unprotected areas after lithography. Wet etching involves immersion in chemical solutions, offering high selectivity but isotropic profiles. Dry etching uses plasma or reactive ion etching, RIE, to achieve anisotropic, vertical profiles. The choice depends on pattern resolution, aspect ratio, and material being etched. Analogously, etching is like chiseling away stone to reveal a sculpture. Wet etching is like using acid to dissolve material. It spreads in all directions. Dry etching is like laser cutting cardboard. It's precise, creating clean vertical edges. Polysilicon is deposited via chemical vapor deposition, CVD, over the gate oxide layer. Subsequent doping with phosphorus or arsenic renders it conductive. The gate pattern is defined using photolithography and etching. The gate length defines the channel length, directly affecting device performance parameters such as threshold voltage and drive current. Analogously, in a MOSFET, the gate is the brain that controls electron flow. We deposit polysilicon, make it conductive with doping, and shape it precisely over the gate oxide. Think of it like putting a bridge across a river. The bridge can open or close to control traffic. Metallization creates the electrical connections between transistors and other components. Physical vapor deposition, PVD, or chemical vapor deposition, CVD, is used for metal films. Lithography and etching define interconnect patterns. Multiple metal layers are stacked with interlayer dielectrics and connected by vias or contact holes. Copper is preferred for advanced nodes due to its lower resistivity. Analogously, metallization is like building a city's road network. We lay down metallic roads to connect houses, transistors. Just like a multi-level flyover, we have several layers of metal connected by vias. Integrated circuit fabrication is a highly controlled sequence of processes. Precision in patterning, cleanliness in the fabrication environment, and accurate layer alignment are essential to maintain high yield and device reliability. Each process step builds on the previous one, requiring stringent process control and monitoring. Now that we've covered the basics of MOS devices, let's talk about the essential building blocks for integrated circuit fabrication. We start with silicon wafer creation. This begins by growing a pure silicon ingot in a crucible using a seed crystal in the Czochralski process. Once the ingot is grown, it's sliced into very thin discs and polished to a mirror finish, giving us the silicon wafers that serve as our starting point. Next comes photolithography, the process of transferring a pattern onto the wafer. We use a mask to define where we want to process the wafer, and UV light is projected through the mask to selectively expose certain regions. This is where photoresist comes into play. It's a special light-sensitive material that changes its solubility when exposed to UV light. In positive photoresist, for example, the exposed regions become soluble and can be removed with a developer solution, revealing the wafer surface underneath. Once we have exposed the desired regions, we can grow silicon dioxide, SiO2, on the wafer surface. This oxide growth can be done either through a wet oxidation process, which uses steam, or a dry oxidation process, which uses pure oxygen gas. It's important to note that this growth consumes some of the underlying silicon. To shape the wafer structures, we use etching. This is the process of removing material, whether it's silicon, SiO2, polysilicon, or metal. Etching can be done with liquid chemicals in a wet process, or with ionized gases in a dry plasma process. When we need to add material rather than remove it, we use deposition. This involves coating the wafer with layers such as silicon dioxide, silicon nitride, polysilicon, or metals, typically using chemical vapor deposition, CVD, or physical vapor deposition, PVD. Finally, to control the electrical properties of different regions, we use ion implantation. Here, we shoot dopant ions, such as boron for P-type or phosphorus arsenic for N-type, into the silicon substrate to create regions with the desired electrical conductivity. Together, these processes, wafer creation, photolithography, photoresist application, oxide growth, etching, deposition, and ion implantation, form the core toolkit for building the layers and structures that make up modern integrated circuits. The diagram shows the example of fabrication of an NMOS transistor. The silicon wafer is first oxidized to create a SiO2 layer on the surface. Using photosynthesis, a window area is selected where an NMOS transistor is to be fabricated. After this, a thin layer of SiO2 is again created using oxidation process, which would be used to have the oxide of the MOS structure. After that, a layer of polysilicon is deposited over the thin CO2 layer. This polysilicon would act as M in the MOS structure. Then, using photosynthesis, etching the polysilicon layer is removed from the area where it is not required. Polysilicon is required only for that part where gate terminal of the transistor is to be fabricated. Then, similarly, the thin SiO2 layer is removed from the region where source and drain of the NMOS transistor is to be fabricated. Here, using doping source and drain regions, concentrations would be changed. As depicted in the first diagram, the N+ doping is created to fabricate the source and drain terminal of the NMOS transistor. The again in CO2 layer is grown and patterned or isolating the source, drain and gate terminal metallizations. After making the window area for contacts of source, drain and gate metallization, and its patterning is done to have the 3 contact terminals as depicted in the last pic.